Okay, so thanks very much. What I was trying to do in the first 4 lectures, if I summarize, was I was trying to say how you might represent spaces in various different ways on a computer, and then how you might compute homology of spaces, and in particular, if you have things like groups, or unfortunately, last lecture I talked about simplicial groups, which mightn't have been so wise, but if you have things like that, and then you take the classifying space, that's really the kind of space whose homology cogent might be interested in. What I want to do today is to try to convince you, and even more than you, me, how these talks, what I'm talking about relates to the cogent group in general. So it's clear that everything I've done has used in a big way, built on what Bettina and Alexander have implemented. When I talk of a group, if it's a finite group and it's polycyclic, I suppose by default I'm using GAP's polycyclic functions. If it's a permutation group, I'm using GAP's permutation group functions. So all of that is being used in the background. So I guess it's clear how what I've been talking about relates to Bettina and Alexander's talks. Let me try to produce a link to the talks of Herbert and Renaud, who talked about Voronoi domains and so on. So I'm going to start with a really embarrassing gap command. So I know it's embarrassing because I tried it this morning, but still, I'm going to VD is going to stand for Voronoi domain, and I'm going to take a Voronoi domain of PSL for Z. In one of the lectures, when I was talking about crystallographic groups and I talked about Voronoi domains, I said I drew a pretty what I thought was a pretty picture, and Herbert asked what did it mean, and it was, depending on how you produce the Voronoi domain, you can have a different combinatorial structure. So let me choose combinatorial structure C, whatever that means, and then I'm going to press return. This is going to take 28 seconds, which is embarrassing, but the most embarrassing feature is that there's no computation going on at all here. What I'm doing is I've taken data from Mathieu Dutour, who traveled with it in an airplane to Galway, put it on my computer, and I'm now loading it into GAP and converting, decompressing. So it's doing nothing. And one of the things that I would like to do is have a function in C or something which is read from GAP, which does this computation live. So a postdoc with Gabi Neber, Sebastian Schoenbeck, he produced such a function, but he produced it in Magma. And then he was going to translate the cohomology functions from HAP to Magma, but that didn't happen. So there is a version that I want in Magma, but I'd like some kind of a version in GAP. And there are different algorithms one can use to do this. Anyway, what's happened? What has been loaded is, going back to Renaud's talk, he talked of Voronoi domains constructed from perfect forms. And so I have a question for the experts, the non-student experts in the audience. If you take a PSL4Z acting on the symmetric matrices, what dimension would you expect the Voronoi domain to be? You're from Renaud's talk, you act on symmetric 4x4 matrices. So I guess there are non-diagonal entries. The numbers to choose are 3 plus 2 plus 1 plus the diagonal. There's probably 10 numbers to choose. So you might expect a 10-dimensional space, except Renaud had he was talking about, the cone. So you can actually slice the cone, so go down by a dimension. You can talk about 9 dimensions. So this should be a 9-dimensional space. Well, a fundamental domain for a tile, for a tessellation of some 9-dimensional space, which the space that Renaud talked about. So let's have a look at that. Let me list in degrees from 0 up to, let's say, 10. There are only, for each degree, let me work out, VD is what I called it. the number of orbits of cells in each dimension. Yeah, because what we have here is a representation of an equivariant, infinite dimensional, non-compact space, but it's a fundamental domain. So what the number of orbits, and I hope I got the right number of brackets. So what we get is there are 3 orbits of 0 cells, 6 orbits of 1 cells, and so on, and it's 9 dimensions. Yeah. So that's what Renaud was talking about. Now, in lecture 2 that I talked about, I gave a lemma of CTC wall, which said that if you have a, I mean, I did it with the torus, but I mean, this is the equivalent of a torus. It's a bit more complicated, and you can. And so, what you have here, if you take the chain complex, the cellular chain complex of this equivariant space, the equivariant space is contractible. So the chain complex is a resolution, but it's not free because there are stabilizer groups. Each of these cells will have stabilizer groups. So now we go to use the functionality of permutation groups and polycyclic groups. And for each, in this case, all the stabilizer groups will be finite. We'll build a resolution for each stabilizer group and piece it all together. So I'll do that now. R is what I'll call the resolution. Now this R equals free G resolution of VD. This might take a little while because now it's actually let me decide how many dimensions. Okay, the thing I'm trying to construct is infinite dimensional. So let me limit. Let's say the first four degrees of the thing. So now okay, that was the wall lemma implemented in a lazy fashion. So nothing's really been computed. It's been pieced together, but no boundary maps have really been computed because you only compute things when you need them. So now let me take my favorite functor. So if you have a module and you want a tensor with a module, you can implement that as a functor, or if you want a HOM to a module, you can implement that too. So if you have, there were questions in the chat yesterday about what happens if you have a cohomology with different modules. So if you can implement it just as a functor, you can apply it. So let me tensor with the integers just to do something simple. This free resolution, but you can do other things, and that produces now a chain complex. And I won't bother making it smaller. I'll just go for it. Let me try to calculate the integral homology of PSL4Z in degree 3. Now it will actually have to do some computation because everything's implemented in a lazy fashion. Now it's going to have to construct some boundary maps and things in order to do any calculation. So I did this morning and it did complete. Yep.
Which package are you using?
Well, so I guess I'm using the HAP package, HAP package, yeah. Plus, which builds on the polycyclic. I mean, I'm using lots of packages, but in particular, all of the packages required by the HAP package. So when you load one package, it pulls in other packages. So for what it's worth, the integral homology in the degree 3 is Z2 plus Z12 plus Z60 plus Z. And what you, I hope, well, I'm not. Let me.
There is really something that I don't understand. So
okay.
If you use really the Borel domain for PSL4,
yeah.
What are you exactly computing? Because you say
I'm
compute the homology of PSL4.
I'm constructing a classifying space for PSL4, a classifying space, an infinite dimensional classifying space, an EG, where G is, and then I'm taking the quotient by G.
But the Borel domain does not give you that.
No. There's a lot of work in what I've done. I mean, it looked like a few seconds here, but it was a year or two for me to program it. I mean,
Yeah, but it's confusing.
well, hang on. Let me go.
You say that you wrote.
No, so I'll go back to the commands. I'll go back to the commands. No, the first thing was K, which I introduced. I introduced K. How do I can go up here. K was the Voronoi domain, VD. VD I called it, VD for Voronoi domain. But then there was this little command that looks innocuous enough, which takes the Voronoi domain and uses the wall trick and constructs resolutions for all the stabilizer groups, and there are rakes of stabilizer groups. I mean, look at all these numbers, and pieces them all together, and then gives us, so there's an extra, the Voronoi domain is just the starting point, and then you have to do a lot of calculation to get the integral homology.
You have an action of the group on the Voronoi domain that is contractible, but then you have stabilizers, and E gets rid of those stabilizers using his permutation.
Yeah, that's it, yeah. So let me just go on.
So it's a very different way that the ways that we use it.
Yes.
Okay, so now I'm going to.
Just about, it is very weird about the dimension 9, because dimension 9 should be for SL4, but for PSL4, I would expect one dimension less.
I mean, if you like lower dimensions, what I could let me take the same. Let me take the same group, and let me just get rid of this C. That C is there just so that it worked in real time, in live. Now I have a different, because we will come on in a moment to talk about deformation retracts and
Why do you use PSL and not SL?
So, as I say, just because that was the group that we, you know, I mean, there's a finite, quite a large finite number of choices, and what I would like, when I was discussing it with Alexander Rahm, what he thought would be better would be to have a library of all these complexes that could be accessed by anybody in the world, which would be good, but I'd also like to have some functions accessible from GAP that really construct them from scratch as well. Yeah, but PSL is because I don't have I can give you SL3 and I can give you, you know, there's a...
You mean constructing the Voronoi domain?
Yes.
Yeah, the Voronoi domain, yeah.
You know that we already have that?
Yeah, but I can't access it from your computer. So if there was a database, okay, then we can talk after. Good. So let me just do a different kind of computation, which might be more interesting. So what I've done there is I've taken techniques, taken the square root of -2, added it to the rationals, -2, thanks, yeah, -2, added it to the rationals, and taken the ring of integers. So instead of Z, I've taken a slightly more complicated ring of integers, but I've made things easier in that I'm doing SL2, 2 by 2 matrices. Yep. And so what you have here, the resolution for that group, it's the same idea. You know, so the homology is whatever it is in degree 4, it's Z mod 12. So what I want to do today is explain how this kind of relates to the cogent community. And I'm going to do it by concentrating on SL2Z for the most part, because the ideas can be communicated for SL2Z, but so I'll go to some slides now. So let's come down to earth with SL2Z, 2 by 2 integer matrices. Okay, so, and let's just focus on one-dimensional cohomology. Yep. So and I want to talk about the one-dimensional cohomology of a group gamma with coefficients in whatever module, gamma module you like, A. the group gamma that I'm going to consider, I want it to be a finite index subgroup of SL2Z. Probably a congruent subgroup for maybe for some parts, but for the most, you can just take it to be a finite index subgroup. So let's take a finite index subgroup gamma of SL2Z to make things concrete. Let's take the module A of homogeneous polynomials. I suppose I'm actually going to be working over Z, but most people might be more interested in C. It doesn't really make a difference, too much of a difference. And I'll explain what the action is. It's just a change of variables, but I'll explain the action. I'll write it down on a slide in a moment. So there's an action of gamma on these polynomials in X and Y with complex coefficients. And then I'm going to not explain the right-hand side here. To speed the talk up, I'm going to regard this as an equality. So there are many people who know way more than I do about modular forms. So if you do know about modular forms, you can think of this as the modular degree K modular forms. And then there's something called an Eichler-Shimura isomorphism, which tells us that the modular form people, what they're interested in can be written in the language of one-dimensional group cohomology. So what I'm going to do is I'm going to think of this as an equals. I'm going to tell you what all these bits are, but in the left-hand side. So I'm not going to talk about it. I'm not going to write down the definition of a modular form and everything. So I want to tell you what the cuspidal part is and the Eisenstein part is and how you might calculate it. But over on the left-hand side. And then what people seem to be interested in there's something called a Hecker operator, which is a homomorphism from this cohomology group to itself. Well, there's one for each, for example, for each integer n. It's a homomorphism from this cohomology group to itself. It actually preserves these subgroups. And so people are interested in Hecker operators, or in particular, they're interested in eigenvalues of Hecker operators. So let me just explain how you might compute the eigenvalues of such a Hecker operator in this context, but in a way that you might not be interested in SL2Z, you might be interested in SL2 in a more complicated ring of integers, and the ideas in principle carry over. In practice, there are things to do. And why might you be interested in this? Let me just not say too much, but there are, there's a basis of eigenforms for modular forms, and so whatever. If you know eigenvalues, you can actually get a basis for this right-hand side. So we won't worry too much about that. I'm going to focus on how on earth do you calculate eigenvalue? What is this Hecker operator, and how do you calculate its eigenvalues? Okay, I'm gonna focus on just two finite index subgroups. So take an integer n, capital N, and then I'll take gamma n, what's that? The principal congruent subgroup. It's all 2 by 2 matrices where the diagonal entries are congruent to 1 mod n and the off-diagonal entries are congruent to 0. And I don't know what this one's called, gamma 0. This congruent subgroup, again, it's a finite index subgroup of SL2Z. It's all 2 by 2 matrices. Where you just have C is congruent to 0. So in this setup, it's straightforward to represent on a computer these matrices and to test if you have a matrix, is it a member of the group gamma n or gamma 0 n? That's just a straightforward test, so there's nothing much to do there. If you want to work with groups, you need generators, and there are various ways to calculate generators for groups. Let me give one way, which is the way that it's implemented in HAP. and let me explain it I'll explain it in the slightly easier case of the principal congruent subgroup, but what I say is extendable to other congruent subgroups. Okay, so if we take the two matrices, S and T, written up there, then it's well known that they are generators for the group SL2Z. So with these matrices S and T, well, first of all, let's construct a new matrix U, the product of S and T. And if you do the calculation, you find that U is of finite order. U to the 6 is the identity. But I'm not interested in generators of SL2Z. I'm interested in generators of a finite index subgroup, which you can do using Reidemeister-Schreier, but there are maybe other ways to do it as well, and I'll describe another way. So let's construct what I'm going to call the cubic graph. I don't know that it's standard terminology, and I'm going to call it T, or T, I suppose that's a curly T. So let me tell you what I mean by the cubic graph. It's a graph whose vertices are the left cosets of the subgroup of order 6 generated by U, the left cosets of this subgroup in SL2Z. So for each coset, you've got a vertex. And let me tell you what the edges of this cubic tree are. So there's going to be an edge joining two vertices. If you have a vertex, this left coset, X times the group generated by U, and Y times the group generated by U, there's going to be an edge joining them precisely if X inverse Y lies in the double coset, something in this element S times something in this group on the left times something in this group on the right. So if this difference lies here, you stick an edge. And then you do some calculations and you draw this tree to get a feel for what it looks like. And there's a piece of the tree. I guess this is a coset of the subgroup U represented by the identity. And then it turns out this is why it's called the cubic tree. There's one edge from U to SU. There's one edge from U to US group generated by U, and there's one edge from the group generated by U to U squared SU, and that's it. And the tree looks like that everywhere. So every vertex it's an infinite tree, and every vertex has degree 3. And then SL2Z acts just by multiplication on the left on this.
Normal name for trivalent.
Is it? Well, okay. Yeah. Then okay. Yeah. Can't you have many trivalent graphs? Well, maybe if it's infinite, I suppose. Yeah.
Trivalent tree.
Tree. Oh, yeah. Okay. Yeah. Okay. Okay. So, trivalent. I took this from Marston Condor's group theory paper, but I mean, yeah. And then you do some calculations, and you find that there's a single orbit of vertices. So under this action, there's only one orbit of vertices, and there's only one orbit of edges. And you can ask what are the vertex stabilizer groups, and they're all going to be conjugate to this group generated by U. And what are the edge stabilizer groups? They're all going to be conjugate to the group generated by the matrix S, which is a group of order 4. And so the way, so we'd like to encode this tree in gap. So what exactly do you have to encode? It's not a lot of information, really. You have to tell gap that we've got a fundamental domain with one orbit of 0 cells, one orbit of 1 cells, and maybe a bit of information about what is the stabilizer of this. Pick a representative for the orbit of 0 cells and give gap the information what's its stabilizer. Pick a representative for the orbit of 1 cells and tell gap what's its stabilizer up to conjugacy, and that's all you have to store. So what was taking 28 seconds, I don't really know why, but from the complex that Mathieu Dutour gave me, it was a more complicated, it was a 9-dimensional complex, but that's all that was being read into the computer. And so, oh yeah, this makes the lecture go a bit faster. If you check, SL2Z acts on the tree, the trivalent tree, but this finite index subgroup, if I stick to the principal congruent subgroup, then you can check that this actually acts freely. If you restrict to this subgroup, there's a free.
The above drawing is representing the quotient of the tree by the action.
What was the first? The second word I did. The what?
The second.
Oh, this here.
It is the quotient of the tree by
Well, at the moment, I'm living upstairs in an equivariant space, so I've got this infinite tree, and I want to be fussy about what's a fundamental domain. I suppose a fundamental domain is a partition of the tree whose union equals the tree and no overlaps.
The quotient will be a point.
Will be in the next one. Yeah. Because I'm still upstairs in the tree. I haven't taken any quotients. Yeah.
For the edge stabilizer, it's like the edges are
not oriented. No, but well, okay. The edge in gap, we're giving the computer the information that there is an edge, an orbit of edges, and that when you act, it flips the edge. That's all but there's no orientation or anything on the tree. But it does, the element does stabilize the edge. That's all. Yeah. The edges aren't oriented. So if you want a fundamental domain for a group which I've concocted nicely now, which acts freely on a tree, then you don't have to go too far. That's going to be a free group. Because actions are free. So you can calculate that in gap. I won't press the commands because. But if you take n equal to 6 and you implement the congruence subgroup, the principal congruent subgroup, gamma 6, and then you can it constructs a fundamental domain. And I've displayed it here. So this is a fundamental domain. And what isn't included in this fundamental domain are the edges which would go out here without a vertex. So this is a fundamental domain minus the edges. So any vertex which has degree less than 3 will have some edges coming out with vertices that will be in a different. So I haven't drawn on those in that picture. And so, can anybody tell me from that picture what is the rank of the free group? That's a mean question, but it wakes people up when you do that. So let me give the answer. I think that what you can do is, if I were to quotient by the action, I'd have a quotient of the trivalent tree, so I'd have a kind of a finite trivalent graph. Yep. And as it's trivalent, any vertex which has degree less than 3 in the quotient is going to have to match up. So really what you have to do is count, for each vertex, count the degree of the vertex, add all those numbers up, and if I got it right, you divide by 2 to get the right count, and you'll get so gamma 6 should be a free group on 13 generators, and gap will give you the generators. So there's a paper 15 or so years ago by, Kulkarni, who, say it again?
Kulkarni?
Yeah, Kulkarni. Yeah, Kulkarni, yeah. Who writes a paper, it's in the Journal of the American Math Talk, who does this, but does it, the same idea, but in general, you should be acting on the upper half plane, and so you should really be taking a two-dimensional complex and so on. So it's the same idea, and you can get minimal generating sets. Yeah. Anyway, I won't go into that. I'll stick to the principal congruent subgroup case. Yeah. So you can extend this idea. Either you can do it the Kulkarni way to get an absolutely minimal generating set, or what's done in gap is we stick with the trivalent tree situation and we get a smallish generating set rather than minimal. It doesn't really matter if it's minimal or not.
Are you claiming that gamma 6 is a free group?
Yeah, because it.
Oh, yeah.
Yeah, because it's free. It's torsion free.
That doesn't mean that it's free. Plenty of torsion-free groups.
Yeah. But this is on 13 generators. Oh, well, okay, but it acts on a tree, so.
Yeah, I guess.
Yeah, it has to be free. I mean, I've never really thought about it before, but I guess if it acts on a tree, it has to be free. Threw me a bit, but am I missing something there? It acts freely on a tree. I think it has to be free, doesn't it? Yeah. So, actually, when I wrote that down, I paused. So maybe, yeah, thank you. Probably free. Rather think about it. Okay. So now what do? We have this fundamental domain, which we can easily input into the computer by hand. You don't need a computer program to do this. And we can use Wall's technique, build resolutions for the stabilizer groups, which in this case are very easy. They're cyclic of order 6 and cyclic of order 4. Piece everything together, and you get a resolution, or if you like, a contractible space for this group G. Now, one of the things I've been trying to get across is that contractible spaces or free resolutions are grand. If you want to do something with them, really you need some way of writing down a contracting homotopy. So when I did PSL for Z, you would have seen, I should have mentioned it at the time, it says a no contracting homotopy available, which means that nobody has yet, related to HAP anyway, thought about how would you contract that space, that infinite space. But let me explain how you contract this easier tree, because trees are easy to contract. But before I do that, we're not actually interested in SL2Z. We're interested in this finite index subgroup. And now I'm going to switch. Okay, so I'm going to switch to gamma 0 because it makes things a bit more fun. This finite index subgroup. So we can find generators for it. So we can represent this group, it's a group of matrices, on the computer. And we've seen when I was talking about manifolds and so on, you can construct covering spaces. Or if you like things more algebraically, the Reidemeister subgroup presentation, it's more or less the same thing, but you can construct covering spaces. And so you can piece this group and and then you take a covering space. So we have this trivalent tree. This finite index subgroup acts on it. So we can piece that together with Wall's resolution, and end up with a contractible space on which this group gamma acts freely. That'll be an infinite dimensional space, but we'll only be interested in first homology or cohomology. So and then what we're interested in is the n equal to 1, really, the first homology of the group gamma 0 of n with coefficients in a module. So what that means is you build your free resolution, you take your module, and you look at the homomorphisms, and Bettina went through this kind of yesterday, from this chain complex, from this resolution to here, and you build a chain complex, and you take the first homology. And then what was this module A? Well, now I'm going to change things slightly. I replaced Z by C by Z. So I'm taking all homogeneous polynomials of degree k minus 2. And the group acts. So the group is a subgroup of 2 by 2 matrices. And it acts on a polynomial. I hope I've got this. It should be kind of, you multiply by A inverse. The action is, if I got it right, it's the inverse of the matrix, is it, I think? Anyway, this is the action. I guess it's one way around. Anyway, this is the action. I have to think about linear algebra, but that's the action. Yep, one way around. So you have a group and you have a resolution, and so you can calculate the first homology. So let me cheat now. Let me do this pre-recorded. So let's do a calculation. Let's construct for this group SL2Z a free resolution. The alt here, there are various ways to construct free resolutions for SL2Z, and I'm just using this particular function to do it. So I'm thinking of that as a contractible space on which SL2Z acts. It's the trivalent tree. Let's construct a congruent subgroup. So let's take, just for fun, n equal to 39 and construct the congruent subgroup gamma equal to gamma 0 of 39. Then let's use the wall as sorry, no. Now let's do something else. So we have EG is a resolution for SL2Z. I'd like a resolution for the finite index subgroup. So it's something like Reidemeister-Schreier is going on here. If you have a module, A, which is a G module, well, it's also a Z gamma module for any gamma, a subgroup of G. And if gamma is of finite index, if this is a finitely generated ZG module, and if gamma is a finite index, you can also regard this as a finitely generated Z gamma module. So that's there's some calculation going on there, or representation on the computer. So now we have a resolution for our subgroup gamma. It might be quite a big resolution because, as Alexander mentioned, taking subgroups, you can get lots of generators and relators and so on. So you'd want some method of simplifying it, and believe it or not, contracting discrete vector fields are a great way to contract things, even if you're up in an equivariant space. If you do it carefully and you've got group actions, you can still contract to a certain degree upstairs using discrete vector fields. Then you have to implement in half a page the module that you're interested in. So the module we're interested in is homogeneous polynomials I want k minus 2 equal to 2, so I want k equal to 4. And then a module has a g action, so this function somehow creates this g action I described and stores it. And then what you do, you take the HOM to integral module of this resolution with coefficients in the module P, and you construct a cochain complex, and then you work out the cohomology in degree 1, and you find that it's Z3 plus Z12 plus so many copies of Z. And so from that, you find then that the first cohomology group, even if you tensor over the complex numbers, the torsion parts disappear, you count the number of zeros, and you find that there are 50 of them. So then you find that this group here is actually of dimension 50. But why do I keep writing this group as 3 summands? It's because there's something called cuspidal. There's a cuspidal part and an Eisenstein part. So I'd better just say what these parts mean using the language of group cohomology only. Okay, so I'll do that. So gamma acts, our finite index subgroup acts on the upper half plane. So now I'm going up to 2 dimensions. It acts on the upper half plane. So we can read from the Wikipedia a favorite fundamental domain for the action. Well, what is the action, first of all? The action of gamma is a group of 2 by 2 matrices on the upper half plane. If Z is in the upper half plane, this is the action of gamma on Z. And then we read from the Wikipedia or somewhere a fundamental domain, and there's this picture that you see everywhere on the internet of a fundamental domain for that group. I want to tell you what cuspidal cohomology means in this particular setting. But before I do that, let me try to draw the picture that I have in my head. So if anybody wants to correct my picture, do, because this is a genuine request, not a yeah. The picture I have then is you have the upper half plane quotiented. So the upper half plane is not compact. You quotient by your group, and so you'll get some kind of surface. But I guess the surface, so it's some kind of surface, but it won't be compact. So the way I would think of that is, yeah, there are bits that aren't there. So that's the way I picture the quotient. A non-compact surface. And, sorry? Well, what width is my D? Oh, have I got two half? You mean I've got two half? No. Well, isn't that from, what's this going from? I think it's going from minus, I think it's going from minus a half to plus a half, isn't it? I haven't given. Ah, yeah, well, yeah. Oh, okay, yeah. Well, it's not quite going from minus. Yeah, thank you. I'm glad you're in the back. Yeah, no, fair point. I mean, it's just, yeah. So then what you can do is you can compactify in some way. And so the way that it seems to be done is using what's called the Borel Circumpactification, which I think we can picture in this situation as just adding on edges to the whatever's not there at infinity. Just add on edges. That's the picture. So what you now have is you have a compactified space, and you have this non-compact subspace, and there's an inclusion. So, and it's all done on a computer with regular CW complexes and so on. So we can, you know, that's good. So what actually is stored in the computer? We store the fundamental domain combinatorially. We store, you know, what are the, there are several orbits of zero cells. There's 1, 2, there are 2 orbits of 0 cells, if I got this right. And there are 3 orbits of 1 cells in the compactified. 3 orbits of 1 cells.
3 is part of the boundary, right?
E3 would be those little, part of the boundary. But there's, I think there's, in this, but yeah, because I'm doing it for SL2Z. Yeah, so there's only one. Yeah, there's only one. At the moment, I'm doing it for SL2Z. That's the picture here is for SL2Z, and that's what you store. And you also have to store the stabilizer groups, and you also have to store which I forgot to say before, how the matrices, just in the fundamental domain, how the matrices are moved by group elements, how the vertices and how the edges are moved by group elements, and that's what's. But it's finite. It's a finite piece of information which you store, and that's what I think would be nice to have well, one, it would be nice to have a database of these things for lots of complicated examples, and 2, some various easily accessible functions for producing them on the fly.
So you're already truncating the cusps. That's I'm not talking to the Borel Circumpactification.
Well, I'm not truncating. No, this is at infinity. That's up at infinity. That's up at infinity.
In the fundamental domain, it looks like you're truncating it, but you could.
Well, I mean, I don't have. It's topologically. It's topologically. 1 minus 1. It's topology. Whew. Now.
Some people like the geometric structure.
No, but I mean because you drew the picture geometrically.
Yeah, okay. I shouldn't have. I mean, because I was going to do it free. I was going to do it freehand, and I didn't know. I was too kind of nervous to. So I used some certain, and I didn't think hard about what. Yeah. Okay, yeah. That's a fair point. Okay, so what do we have? We have an inclusion of the boundary. So the boundary of the compactified space is something, and the boundary includes. What am I talking about? Let me. What have I done there? Let me just. That's nonsense, isn't it? Let me do it again. Is it right? The boundary. So hang on, yeah, but I'm.
From cohomology of XPS to the boundary of XPS, but cohomology of XPS is the same as cohomology of X, so you can write it down.
Yeah. So I'm writing the cohomology of XBS is, yeah, okay, yeah. So there was something, thanks, yeah. These two are kind of homotopy equivalent, so we can regard them as the same. Yeah. So the XBS contains the boundary. So there's a map from the boundary into XBS, and so on cohomology, the arrow goes in the opposite direction, and then you can define what people were talking about last night over the meal of interior something or other cohomology, or you can, in this context, I think you can just say cuspidal in this particular setting. So the cuspidal cohomology is this kernel. And then what are these summands? Well, we can take these summands as the two of them, whatever they mean to number theorists, group theoretically, the two of them together constitute the cuspidal cohomology. So we can calculate the cuspidal cohomology using gap. So here's a computation by it's not, so what's going on here? I've got a -2 in the.
No, I forgot what that was.
Oh, all right, okay, yeah. So here's just rather than give you a long kind of slide of 5 or 6 commands, this is a command that sticks things together, and it calculates the cuspidal cohomology homomorphism of a finite index subgroup in degree 1, the first cohomology, and then the k is the weight, or the, yeah. And then you find the kernel, and you find that it's 1, 2, 3, 4, 5, 6, so it's, well, I'm actually working over the integers, but we can pretend we're working over the complex numbers. So that's C the dimension 6. So this part, these two are kind of isomorphic sometimes, so this is C3. So that can be done. There are more efficient ways to do it in this way, but the way I'm explaining, I believe, generalizes in principle. It's an easy generalization in principle. In practice, there's a lot of efficiency questions that you have to kind of work on. So what's a Hecke operator? So let's take a finite index, or maybe a congruent subgroup of SL2Z. Take a matrix in SL2Q, and then look at the intersection of your gamma with the conjugate of gamma. And hopefully that will be of finite index in SL2Z, otherwise things won't work. But that's the only bit where things have to be a bit careful. And then what you have, if I've written this down correctly, gamma prime is certainly a subgroup of gamma, that's for sure. Gamma prime is the intersection of gamma with something. So gamma prime is certainly a subgroup of gamma. And also, if you conjugate G inverse gamma prime G, that's also going to be a subgroup of gamma. So these are just subgroup inclusions. That's not. And then here you really have a homomorphism, which is conjugation. So now what you do is you press buttons, and I'll write it down for k equal to 2 just because I can write z. The module of homogeneous polynomials of degree 0 is c, and instead of c I'm going to write z because I'm working over z. So then, at least mathematically, if I've done this correctly, what am I doing? Oh gosh. Yeah. No. What's? Yeah. Hang on. Let me go here. So the middle. So this is just a homomorphism of groups. So cohomology should give me a induced homomorphism. This is just a homomorphism of groups. So I don't know where it is over here, is it? No, here. I don't know if I got this right. That should give me a homomorphism, or the other one. And then there's something called the transfer homomorphism. in group cohomology, which has to be implemented. And when you combine all of this, you actually get a homomorphism from this group to itself, which could be represented by a matrix. And then you could use gaps, give me eigenvalues function to find the eigenvalues. Okay, so let's take for T, G. So up to now, I just said take an element G in your SL2Q. Let's take a particular element G. Let's take G to be the matrix N0, 0, 1 over N. It's a particular one. And then let's just define Tn to be T for that group. Oh, gosh. He's still there. Oh, gosh. Anyway, whatever. Oh, yeah. So the trivalent tree, or cubic tree in some group theory paper, but trivalent tree can also be thought of, maybe more helpfully, as lying inside the upper half plane, and I've drawn it there in relation to the rest. And let me just go back, because I'm being too kind of hand-wavy. I mean, everything transfer is actually easy enough. If you look at the definition, you can just implement it. But, and inclusions are probably easy enough, because inclusions of subgroups. But here, you really have a homomorphism. Yep, it's not cellular. Just like when we talked about the diagonal approximation. So you do have to think, and one way or another, you have to come up with a contracting homotopy. So there are different ways of producing contracting homotopies, and the one that I'm going to talk about, have been talking about, is discrete vector fields. So there's our tree. Can we write down an algorithm for a discrete vector field on that tree? That sounds kind of trivial, because any tree is clearly contractible. On the computer, you do have to remember that these vertices are actually left cosets. And you have to, given the left coset, you have to tell the computer where does the arrow go to, which direction. And for any left coset, there'd be 3 possible directions. So you have to write down an algorithm. And the algorithm, well, maybe before that, you can actually contract the upper half plane onto this tree in a SL2 equivariant fashion, so you can work with both. And then you have to think of a contracting homotopy. And so the picture is obvious, but you do have to write down what's the algorithm that you give the computer to specify these. Give them some vertex down here, which is represented by a matrix. What does that edge, what vertex does that edge point to? So you have to write down that algorithm. And once you've done that, you'll have a contracting homotopy, which is done for SL2Z, and then so then you can do things like you can take this congruent subgroup. You can take, don't know what I mean by P. All right, yeah. What am I doing? I'm taking the congruent subgroup. Yeah, and here is a typo. This is actually Hecker operator weight 2. I changed the name. When you're designing functions, you don't want the input to be too complicated. On the other hand, so for this, I've changed the name. This is Hecker operator weight 2, because I was just using the module Z, but you can equally well use other modules. It's just, it's just an implementation. So, and then what I'm calculating then is the Hecker operator. Yeah, unfortunately, I shouldn't be using capital N. I'm using capital N in a different sense now. What I mean by N is the degree of the cohomology. Now I've switched. Okay, so in the cohomology of degree 1 with p equal to 2, you ask for the Hecker operator, and it gives you. This is on the whole cohomology. And you get it as a homomorphism, which you convert to a matrix, and this is the matrix representing the Hecker operator T2. And then you can ask gap for eigenvalues, so on. And then you can do it again for, I don't know why I chose p equal to 5 for some reason, and do it again, and you get a different matrix. You can ask for its eigenvalues, or you can do computations and observe that they commute and so on. So that's...
What is p is the...
Yeah, the notation was...
P
P,
is the little n.
yeah, what about p is the P is yeah, my example doesn't match what I wrote on the slides. So my P is this should be P. Oh, sorry, that should be P. Yeah, things don't match up with them. And
this was the Heck operator on the whole thing, you said?
this is yeah, the cuspidal part plus the cuspidal part plus the Eigen, the Eisenstein part. Yeah, on the...
Fifth dimension.
Hmm?
Wasn't it fifth dimension?
No, that was a different... I can't remember what that... There was a 50, I can't remember.
Hospital was 3-dimensional.
What was... No, but I think I might have... let me have a look. That was 50. What was this, though? But what was I doing?
Weight 6, okay, that's different.
Oh, yeah. This was just to show off that you can use modules. Yeah. So I... And then I... Yeah. And very, very quickly, in a minute then, what happens if you wanted other groups? So, for example, Mathieu de Tour has given me, no, I should say that Alexander Rahm and Sebastian Schoenberg have given me fundamental domains and all the information for dealing with a finite number of these kind of groups, in particular this one. So let's look at SL2, whose entries are in the Gaussian integers. That acts on the upper half space. So you've got the complex plane, and you've got the positive part of the real line. And then the details aren't important. You can read them afterwards, or if you don't know them already. But you can introduce some notation. You can introduce a j, which satisfies j squared equal to -1, and this square root of -1, which is I times j would be equal to -ji, and so on. And then you can write z comma t as z plus tj in that language. And then the action is, if I got it right, what you think it should be. It's except I've probably got... I think I should be taking the inverse or something of this matrix. So I've probably got up to an inverse. That's the action is something like that. Then you need a fundamental domain. So now you're in three-dimensional space. So we saw this in Herbert's talk. So a fundamental domain in this particular case is this portion of the hyperbolic 3 space. Above this is a sphere. And then, as in the case of SL2Z, where you can contract the upper half space onto the trivalent tree, in this case, you can contract upper half space onto a two-dimensional complex. So it's the two-dimensional complex which is more convenient to install recode in HAP. So you can do commands like this, constructor free resolution, and then if you wanted with, for this group with homogeneous polynomials of degree 24, whatever, you can work out the cohomology and homology. But I can't work out Hecker operators yet. This is the place I want to stop. Why can't I work out Hecker operators? Because I haven't yet, in this setting, implemented contracting homotopy. I know that this upper half space is contractible, and I know that there's a deformation retract which is contractible. But if I really want to do the calculations, I have to have a way of telling the computer that it's contractible. I have to give the computer a formula for a contracting homotopy. So, as I say, one method would be possibly to use discrete vector fields. Another method that Mathieu de Tour has proposed is You use techniques from compressed sensing. It's the same kind of thing. It's linear algebra in some way. Or you one way or the other, you come up with a way of writing down a contracting homotopy. Then automatically all the functions that are there in gap will apply.
I mean, if you cut this in the right in the middle, it would be exactly the tree. You take a slice of it.
Oh yeah.
So if you can just converge to the center,
in some of these cases, I mean, this is an amalgamated product of amalgamated products. In one of the earlier lectures, I just briefly said, you know, if you have graphs of groups or groups acting on complexes and the wall perturbation technique, if you know, so you can in this example you can actually decompose this group as a product of groups which are finite groups for which you have contracting homotopies, and then Wall's lemma pieces everything together and the formula just falls out. But that formula mightn't be as efficient as something geometric. And in general, I don't suppose you can express one of these arithmetic groups you know, automatically. It'd be more complicated. But yeah, but I mean, that's another way to do it. But really, once there's, so that's a kind of a, what I think is an interesting question, how you contract the upper half space. It's kind of obvious, but the algorithm for it needs thought. And yeah, merci. Okay.